Part 2 of 2B1, horizontal asymptotes, and we're going to run through this fairly quick. So first of all, unlike vertical asymptotes, which I have illustrated here, these two asymptotes here are vertical asymptotes, where we have local behavior as we go from the left bound it approaches 1 and we go from the right bound it approaches 1. That would make a vertical asymptote at x equal 1. We're now going to look at the end behaviors of what's going on with the graph. And as you can see, as x approaches infinity, y is going to approach 0. And the same thing, as x approaches negative infinity, y will also approach 0. That makes that a horizontal asymptote. So identifying horizontal asymptotes, we're going to take a look at the rational function and see what's going on with the numerator-denominator relationship. If the degree of the numerator is less than the degree of the denominator, say we have an x squared on top, but we have x cubed on the bottom, our asymptote is going to be y is equal to 0. If the degree is greater than the degree of the denominator by 1, the numerator is by 1, there's no horizontal asymptote. You're going to have what is called an oblique or slant asymptote. And this is this case here. Now, I've been looking at the notes. I inherited all the notes that the school gave me. And for on-level pre-cal, it looks like they're not investigating slant asymptotes. I'm going to investigate that further when we have our teacher in service. But I found that a little curious because at my last school, we definitely taught slant asymptotes not just in pre-cal, but in Algebra 2 as well. So I'm curious on that. But if we don't teach it here, we just don't teach it here, but you will see it in college. All right, so the degree of the numerator is equal to the degree of the denominator. We're going to have a horizontal asymptote that equals to the leading coefficient. So in instance, the ratio of the leading coefficients. So if I had like 6x squared blah 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 over 2x squared blah 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 blah, I'm going to have a y is equal to 3 horizontal asymptote, which is illustrated right here. Now the thing about asymptotes, horizontal asymptotes, is that unlike vertical asymptotes where they never cross, okay, this will never cross. We have that domain restriction. Not so much for horizontal asymptotes. They can cross the asymptote. It's the end behavior we have to watch out for. It's going to approach your horizontal asymptote. Now, again, look at the examples we give you. That doesn't happen too much, but I will assign some book problems where that will occur. All right, so let's go ahead and find the horizontal asymptotes on these. So going back to our rules, and they gave me, I saw on your notes, something about Bobo eats something or whatever. It's an acronym or mnemonic. I'm not a big fan of this one because the one that I read in your notes doesn't talk about oblique or slant asymptotes. So that's not going to serve you any, when you take your freshman math courses, which many of you are going to be doing next year, it's not going to serve you any good. So I'm here to help you prepare for college, and some of these tricks that we give you in high school sometimes don't work out too well. So what we have here is we just have a constant on the top and a quadratic on the bottom. So this is going to be the degree is bigger in the denominator. Our horizontal asymptote is going to be y is equal to 0. Here we have an x squared on top and an x on the bottom. You're not going to have a horizontal asymptote, but you'll have an oblique. And most teachers, I would say the vast majority, call them slant asymptotes. Okay, but again, it looks like for our on-level pre-cal, this was omitted. I'll think on that. I may just rewrite it and throw it in. All right, so this our last one. We have a first degree. We have two first degree polynomials on the top and on the bottom. That means these are going to be the same degreed polynomials. So what we're going to do is we're going to take these two leading coefficients, just basically create a fraction, and we have a horizontal asymptote at y is equal to 2. Okay? So let's put it all together. So now I have a function, a rational function, x minus 2 over x squared minus 4. And the first thing we tend to always want to do is check out the domain. We have a domain restriction. When we do our difference of two squares, set this equal to 0, we know that x cannot equal to 2 and x cannot equal to negative 2. That's our domain restriction. Let me go ahead and write this in interval notation. You can do this in set notation as well. So I have from negative infinity to negative 2, union from negative 2 to 2, union from 2 to infinity. Okay, so that's my domain. I'm going to have a vertical asymptote. So when I factor this, I'm going to have x minus 2 over x minus 2 times x plus 2. That, of course, cancels these out. That creates a hole right there, but I do have a domain restriction at both of these, but I have a vertical asymptote at x is equal to negative 2. So I have x is equal to negative 2 as a vertical asymptote. Our other hole is going to be at x equal to 2. We do have a horizontal asymptote. This is bigger on the bottom, so it's going to be y is equal to 0. And to find the x-intercepts, we're going to simply, well, when that cancels out, we have 1 up here. We don't really have an x-intercept, okay? Y doesn't equal, x doesn't equal to 2, so that's a domain restriction, so there's no x-intercept. But a y-intercept, we substitute zeros into our function. We can substitute up here, over here, doesn't really matter, and we're going to get 2 over 4, all right, which is 1/2. So it's going to be 0 and 1/2. One more example. So here we go. First thing you want to do is probably factor this and find the domain. Factoring, what times what is equal to negative 4, and add together negative 3. That's an easy one, x minus 4 and x plus 1. Here we have what times what is equal to negative 2, and add it together gives you a split the middle. That's going to be, or you could just do mental math or in your head, 2x minus 1, and that's going to be x plus 1. Okay? So domain restrictions, looks like we can't have x unable to equal to negative 1, and x cannot equal to 1/2. All right, so our domain restrictions, I'm going to start, I'll use interval notation again. 0 to negative 1, union from negative 1 to 1/2, union from 1/2 to positive infinity. Vertical asymptotes. Well, we created a hole at x equal negative 1. So that's going to leave 2x minus 1. We're going to have a vertical asymptote of x is equal to 1/2. Okay, and our hole is going to be x is equal to negative 1. Horizontal asymptotes. Well, these are the same, 2 on 2. So what we're going to do is we're going to create the ratio of, that's a 1 right there, leading coefficient of 1 over 2. Right there. So horizontal asymptote, y is equal to 1/2. That's going to be the line y is equal to 1/2. X-intercepts, well, I'm going to look up here because I could have wrote this like this. Okay, x minus 4 over 2x minus 1. And when I solve for that, I'm going to get basically 4 over negative 1, so 4. So I'm going to have an x-intercept of 4, 0. And when I solve for my y, I'm going to get 4. All right? Okay. That is pretty much it. You're going to get lots of practice on this and be proficient. That's all I can say. There's going to be plenty of homework and additional book problems on these. Okay, we'll catch you on the next lesson.